This lesson looks at rotations, and you've heard the term rotation before. You think spinning around in circles, and you would be the center of rotation. So here you're standing, and you're spinning something around, and now we want to describe whatever's on the end point of what you're spinning around. So that's what we're going to do today using a couple different transformations that are given below. So we have a rotation of 90 degrees, which means you're standing here and you want to go directly 90 degrees. So this is the rotation of 90 from the blue point to the red point. And the translation given takes AB, your starting point, your initial point, and it takes it to negative B comma A. So if you're rotating by only 90 degrees, you flip your x and y values, and you make the new x value negative. For a rotation of 180 degrees, here's the rule that is given. You leave A and B the same, but you're actually flipping the sign. So you're leaving x and y the same, and you're making them both negative. For a rotation of 270 degrees, it's very similar to the one of 90 degrees, where you're taking the x and y values, or in this case the A, B given, and you're flipping them, but then you're going to change the sign of the new y value, so you're going to make it negative. Up front, these rules may seem silly, but we're going to look at them extensively in class and describe how these work and analyze them a little bit more. But for now, I'm just asking you to use them, and we're going to do those in some examples coming up. I've already given you the directions on how to translate anything by 90 degrees, 180 degrees, or 270 degrees. But you're not always going to have those, so I want you to be able to construct them on your own. Looking at this coordinate plane, I've got quadrant 1, 2, 3, and 4 as labeled. X values in quadrant 1 are positive, so are y values, so I've labeled this as positive, positive. All of the ordered pairs in this quadrant are going to be positive, positive. Similarly, these are all the negative x values, positive y values, so I have negative, positive, and negative, negative, positive, negative. We're going to use those facts. And one thing you need to remember is you always are going to switch x and y unless you're rotating by 180 degrees. That's the only situation where x and y stay the same. So let's start off with some point. And I'll start off with a point 2, 3. To rotate this point by 90 degrees. By rotating this point 90 degrees, I will end up in the second quadrant. So a rotation of 90 degrees, or 270, tells me that I need to switch x and y. So 3, 2. But now, the signs in quadrant 2 are negative, positive. So it's going to be negative 3, positive 2. Now I can plot that point. What this tells me is, when I take the point 2, 3, and I rotate it about the origin by 90 degrees, it's going to end up at this point, negative 3, positive 2. So again, here's my center of rotation. And you're taking this point, imagine like a string with something hanging off the end of it, and you're spinning it 90 degrees, and there it goes. Now I can do the same thing for 270 degrees. Which is, again, I reverse 2 and 3 and make it 3, 2, but then I have to change the signs. However, the signs down here are positive, negative, so we have 3, negative 2. So when I go to plot that, 3, negative 2 shows up right here. And again, 270 degrees looks like that. The only oddball out is the 180 degrees. So when I have to rotate 180 degrees, I don't change x and y, but I do change the signs. So I can take 2, 3 and make them both negative. Negative 2, negative 3. There's my point. And that represents my rotation now of 180 degrees. So I start off at my initial point. My terminal point, 180 degrees later, is now in my third quadrant. In this example, we're given the vertices of a triangle, and we're asked to rotate this by 90 degrees. So the first thing I'm going to do is plot the triangle. Here we have point X, point Y, and finally point Z at 1, 5. And I'm going to connect this to draw the figure. Now I'm rotating this about the origin of 90 degrees. A rotation of 90 degrees, remember, takes the xy values, and since it's 90 degrees, we're going to flip x and y, so we're going to make it y comma x, and take the negative value of the y as my new x value. We'll start by finding x prime. So I'm going to swap my x and y values. We had -1 and 0. And I have to reverse the sign of the new x value. So this is going to become +1. It was -1. Swapping 3 and 1, we get 1 comma 3. And opposite sign for the x value. Swap 1 and 5, 5 comma 1, and make 5 the opposite value. Now I can go ahead and plot all of these points. I'm going to use a different color. So I have +1, 0. Here's my new x value, so I'm going to call that x prime. -1, +3 is my y prime. And then finally, z prime is -5, +1. So right there. Notice how I've labeled all the points. I'm connecting my triangle. Triangle x prime, y prime, z prime. And this is the rotation of 90 degrees. Let's do one more before you try this on your own in your notes. And this is a rotation of 180 degrees. When we're rotating by 180 degrees, we take our original coordinates and we just take the reciprocal sign of both x and y, or a and b in this case. So this is going to be -a, -b. We're not swapping a and b at all. They stay the same. This is that special case. So I first want to start by plotting the vertices of this triangle. Once you have your triangle plotted, make sure that you do go through and label all of these points. So we had k at 0, 5, L at 2, 4, and M at -2, 4. And now, at this point, it's pretty much a piece of cake, because what you're doing is you're taking the same coordinates, but just negating each of them, making them negative. Obviously, -0 is the same as 0, so I'm just going to leave it as 0. Please do not write -0. We have -2, -4, and -2 becomes +2, -4. Now that I have my k prime, l prime, m prime, let's go ahead and plot them. We have 0, -5, right here as our k prime, -2, -4 as m prime, and then finally 2, -4 as l prime. So we have our image of our original triangle. You might notice something, that not only is this a rotation about the origin of 180 degrees, but this actually could be described as a reflection across the x-axis. And that comes up very often, so you'll be able to recognize that later on. Now I want you to try question C in your notes on your own, and we will discuss this in class. I'll expect you to have it done. Next up is rotational symmetry. This is where we can take any figure, so for example the pictures that I have shown below, and you can rotate it in some fashion that it rotates and fits right back onto itself. So as an example, if I were to take this first picture of the Twitter birds, I guess, and rotate them by 90 degrees, you could rotate it and insert it back onto itself, so it repeats itself around. So it's symmetric about the origin. And we're going to figure out if figures have rotational symmetry or not in a couple examples in a bit. These questions are going to start off a little bit more basic, and really I just want you to recognize if these have rotational symmetry or not, and then describe its symmetry by stating how many degrees you must rotate to actually achieve fitting it back on itself. So we're going to start with number 2. Start by drawing your lines of symmetry. So I'm going to connect these vertices, and notice I've just chopped it in half and I have 2 symmetric sides. I can also chop it in half this way and have, again, symmetric sides. So now I have the center of rotation right here, and I have 90-degree angles between each of these lines of rotation. So this means that how many degrees should it rotate to achieve symmetry? Well, that's 90 degrees. Let's backtrack to number 1. Again, I'm going to do the same thing. cut it up into its symmetric pieces. So I can cut this figure in half 3 different times, and it's going to meet up at the center point right here. Now from this center point I have 6 lines going out, so 360 divided by 6 is equal to 60. So this has a degrees of rotation of 60 degrees symmetry. In general, you can always take 360 degrees and divide it by the total lines of symmetry that we had. So we had 6 in this case, which in fact happened to be the same amount of vertices. So in number 4, what this turns into, rather than drawing all of these out, I'm going to count the vertices. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 vertices. So I can take 360 degrees, divide that by 17, and this will give me how many degrees I must rotate to achieve symmetry. I get a decimal, and it's approximately about 21 degrees to achieve rotational symmetry. Notice that I skipped number 3, and the reason I skipped this is you can't actually find any symmetries in this one. If I were to cut these in half, I do not have 2 symmetric reflections, so this one does not have rotational symmetry. While I can take this figure and rotate it around 360 degrees and put it back on itself, remember the rule is that you have to be able to rotate less than 180 degrees for something to have rotational symmetry. In class, you're going to be figuring out the rotational symmetry of different figures, and I'd expect you to know how to calculate using the method of 360 degrees divided by the total number of lines of symmetry.